vibrating rising main bus bar system can present significant challenges, especially in critical environments. To effectively troubleshoot the vibration, firstly, identify the possible causes of the vibration. Common causes include loose connections on bus bars or terminals, faulty equipment connected to the system, such as transformers or switchgear, harmonic resonances caused by high currents or switching transients, excessive current draw or load imbalances, and mechanical resonance of the bus bar support structure. Secondly, conduct a visual inspection. This involves several steps. Check for any loose bolts or connections on the bus bars. Examine the connected equipment for any signs of damage or overheating. Inspect the bus bar support structure for any cracks, distortions, or loose components. Thirdly, electrical measurements should be taken. Use a clamp on ammeter to measure current draw and identify any imbalances. Perform harmonic analysis to detect any excessive harmonic content. Use a vibration analyzer to measure the frequency and amplitude of the vibration. Fourthly, implement troubleshooting steps based on the findings from the inspections and measurements. These steps include the following. Tighten loose connections. Ensure all bolts and connections are securely tightened. Inspect connected equipment. Isolate and test any suspected faulty equipment to determine if it is the source of the vibration. Mitigate harmonic resonances. Use harmonic filters or passive filters to suppress excessive harmonics. Reduce current draw or load imbalances. Redistribute loads or upgrade equipment to handle higher currents. Reinforce the bus bar support structure. Strengthen or replace any weak or damaged support components to prevent resonance. In addition to the troubleshooting steps, consider these additional factors. Ensure the bus bar system is adequately grounded. Check for any electromagnetic interference from nearby equipment. Consult with an electrical engineering professional for further analysis and recommendations. It is important to adhere to safety precautions throughout the troubleshooting process. Wear appropriate personal protective equipment, or PPE, during the troubleshooting process. To energize the system before performing any electrical work. Follow hospital safety protocols and lockout or tagout procedures. Let's delve into each of these points in more detail. Loose connections can create a point of high resistance, leading to heat generation and vibration. Visually inspect each connection point, paying close attention to the tightness of bolts and nuts. Use a calibrated torque wrench to ensure that connections are tightened to the manufacturer's specified torque values. Over or under tightening can both lead to connection problems. Over tightening can damage the connection hardware, while under tightening can leave the connection loose. Faulty equipment, such as transformers or switchgear, can introduce vibrations into the system. These vibrations can be transmitted through the bus bars. Inspect all connected equipment for signs of damage, overheating, or unusual noises. Use thermal imaging to identify hot spots, which can indicate potential failures. Isolate suspected equipment and test it independently to determine if it is the source of the vibration. Harmonic resonances can occur when the frequency of electrical harmonics in the system matches the natural frequency of the bus bar structure. This can lead to amplified vibrations. Perform a harmonic analysis using a power quality analyzer to identify the presence and amplitude of harmonics. Consider using harmonic filters or passive filters to suppress excessive harmonics. These filters are designed to attenuate specific harmonic frequencies, reducing their impact on the system. Excessive current draw or load imbalances can also cause vibrations. High currents can create electromagnetic forces that vibrate the bus bars, while load imbalances can lead to uneven current distribution and increased stress on certain parts of the system. Use a clamp on ammeter to measure the current in each phase of the bus bar system. Compare the current values to the rated capacity of the bus bars and identify any significant imbalances. Redistribute loads to balance the current draw across all phases. If necessary, upgrade equipment to handle higher currents. The bus bar support structure plays a critical role in damping vibrations. Weak or damaged support components can allow the bus bars to resonate, amplifying vibrations. Inspect the support structure for any cracks, distortions, or loose components. Strengthen or replace any weak or damaged components. Consider using vibration damping materials to reduce the transmission of vibrations through the support structure. Proper grounding is essential for preventing electrical noise and reducing the risk of electrical shock. Ensure that the bus bar system is adequately grounded according to applicable electrical codes and standards. Check the grounding connections for corrosion or looseness. Use a ground resistance tester to verify the integrity of the grounding system. Electromagnetic interference, or EMI, from nearby equipment can induce currents in the bus bars, leading to vibrations. Identify potential sources of EMI, such as variable frequency drives or radio transmitters. Shield the bus bars or relocate the interfering equipment to reduce EMI. Consult with an electrical engineering professional for further analysis and recommendations. A qualified engineer can perform a detailed analysis of the bus bar system and provide expert guidance on troubleshooting and resolving vibration issues. They can also help to ensure that the system meets all applicable codes and standards. Always wear appropriate personal protective equipment, or PPE, when working on electrical systems. This includes safety glasses, gloves, and insulated tools to energize the system before performing any electrical work. This is the most important safety precaution. Follow hospital safety protocols and lockout or tagout procedures to prevent accidental energization of the system. This includes properly identifying all circuits and equipment, disconnecting power sources, and applying locks and tags to prevent unauthorized reconnection. Remember that working on electrical systems can be dangerous. If you are not qualified to perform the work, contact a qualified electrician. By following these steps, you can effectively troubleshoot a vibrating rising main bus bar system in a hospital and ensure the safe and reliable operation of the electrical system. When addressing harmonic resonances, several types of filters can be implemented. Firstly, passive filters are tuned to specific harmonic frequencies and consist of inductors, capacitors, and resistors. They are relatively simple and cost-effective, but can be bulky and may require retuning if the system characteristics change. Secondly, active filters use power electronic components to inject current waveforms that cancel out the harmonic currents. They are more complex and expensive than passive filters, but offer better performance and can adapt to changing system conditions. Thirdly, hybrid filters combine passive and active filtering techniques to achieve a balance of cost and performance. They typically use a passive filter to handle the dominant harmonics and an active filter to compensate for the remaining harmonics. When redistributing loads to reduce current imbalances, consider the following strategies. Firstly, analyze the load distribution across all phases of the bus bar system. Identify any circuits or equipment that are drawing excessive current from a particular phase. Secondly, shift loads from heavily loaded phases to lightly loaded phases. This may involve rerouting circuits or relocating equipment. Thirdly, use load balancing transformers to automatically balance the current flow across all phases. These transformers are designed to compensate for load imbalances and maintain a balanced voltage supply. When reinforcing the bus bar support structure, consider the following materials and techniques. Firstly, steel is a common material for bus bar supports due to its strength and durability. Ensure that the steel supports are properly coated to prevent corrosion. Secondly, fiberglass reinforced plastic, or FRP, is a lightweight and non-conductive material that is suitable for bus bar supports in certain applications. It offers good resistance to corrosion and can be molded into complex shapes. Thirdly, vibration damping materials such as rubber or viscoelastic polymers can be used to reduce the transmission of vibrations through the support structure. These materials are typically applied to the contact points between the bus bars and the supports. When checking for electromagnetic interference, or EMI, consider the following sources and mitigation techniques. Firstly, variable frequency drives, or VFDs, are a common source of EMI due to the switching of power electronic components. Use shielded cables and filters to reduce the EMI emitted by VFD. Secondly, radio transmitters can also generate EMI that can interfere with electrical equipment. Relocate the transmitter or shield the bus bar system to reduce the interference. Thirdly, power lines and electrical equipment can radiate EMI. Maintain a safe distance between the busbar system and potential sources of EMI. When consulting with an electrical engineering professional, be prepared to provide the following information. Firstly, a detailed description of the vibration problem, including the location, frequency, and amplitude of the vibration. Secondly, a schematic diagram of the busbar system showing the location of all components and connections. Thirdly, electrical measurements such as current, voltage, and harmonic content. Fourthly, any relevant historical data such as maintenance records and previous troubleshooting efforts. Remember that safety is paramount when working on electrical systems. Always follow proper safety procedures and wear appropriate personal protective equipment. If you are not comfortable working on electrical systems, contact a qualified electrician. To further elaborate on the grounding considerations, it is crucial to understand the role of grounding in mitigating electrical noise and ensuring safety. Firstly, the grounding system provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices to quickly trip and prevent electrical shock. Secondly, it helps to reduce electrical noise by providing a reference point for the voltage potential. This can improve the performance of sensitive electronic equipment. Thirdly, it protects equipment from damage due to lightning strikes and other transient voltage surges. When evaluating the grounding system, consider the following aspects. Firstly, the size and material of the grounding conductors. The grounding conductors should be sized according to applicable electrical codes and standards. Copper is a common material for grounding conductors due to its high conductivity and corrosion resistance. Secondly, the number and location of grounding electrodes. The grounding electrode should be installed in accordance with applicable electrical codes and standards. Multiple grounding electrodes may be required to achieve a low ground resistance. Thirdly, the connections between the grounding conductors and the grounding electrodes. The connections should be tight and corrosion resistant. Use appropriate connectors and techniques to ensure a reliable connection. In addition to the above considerations, it is also important to regularly inspect and maintain the grounding system. Check for corrosion, loose connections, and damage to the grounding conductors and electrodes. Test the ground resistance to verify the integrity of the grounding system. If the ground resistance is too high, take corrective action to improve the grounding system. Another important aspect of troubleshooting a vibrating busbar system is to understand the different types of vibrations that can occur. Firstly, mechanical vibrations are caused by physical forces such as rotating machinery or impact loads. These vibrations can be transmitted through the busbar structure and amplified by resonance. Secondly, electrical vibrations are caused by electromagnetic forces, such as those generated by high currents or switching transients. These vibrations can directly excite the busbars and cause them to vibrate. Thirdly, acoustic vibrations are caused by sound waves, such as those generated by nearby equipment or machinery. These vibrations can be transmitted through the air and cause the busbars to vibrate. When troubleshooting vibrations, it is important to identify the source and type of vibration. This can help to narrow down the possible causes and develop effective solutions. Use a vibration analyzer to measure the frequency and amplitude of the vibration. This information can be used to identify the resonant frequencies of the busbar structure and to determine the effectiveness of vibration damping measures. Consider using vibration isolation techniques to reduce the transmission of vibrations from the source to the busbars. This may involve using vibration mounts, flexible connectors, or other vibration damping materials. Regular maintenance and inspection of the busbar system can help to prevent vibration problems. Check for loose connections, damaged components, and signs of overheating. Tighten loose connections, replace damaged components, and clean the busbars to remove dirt and debris. By following these steps, you can effectively troubleshoot and prevent vibration problems in a busbar system. Remember to always prioritize safety when working on electrical systems. Wear appropriate personal protective equipment to energize the system before performing any work, and follow hospital safety protocols and lockout or tagout procedures. In situations where harmonic distortion is suspected, understanding the total harmonic distortion, or THD, is very important. THD is a measurement of the harmonic content present in a voltage or current waveform. It is expressed as a percentage of the fundamental frequency component. High levels of THD can cause a variety of problems, including overheating of equipment, increased energy losses, and malfunction of sensitive electronic devices. To reduce THD, consider the following measures. Firstly, use harmonic filters to attenuate specific harmonic frequencies. Secondly, use power factor correction equipment to improve the power factor and reduce the current drawn from the power system. Thirdly, use line reactors to reduce the rate of change of current and voltage, which can help to dampen harmonics. Fourthly, use shielded cables and filters to reduce the emission of harmonics from electronic equipment. In addition to reducing THD, it is also important to ensure that the power system is properly grounded. A properly grounded system can help to reduce electrical noise and improve the performance of sensitive electronic equipment. When troubleshooting a vibrating busbar system, it is also important to consider the environment in which the system is installed. Factors such as temperature, humidity, and air quality can affect the performance and reliability of the system. High temperatures can cause the busbars to expand and contract, which can lead to loose connections and vibration. High humidity can cause corrosion of the busbars and connections, which can also lead to vibration. Poor air quality can cause the busbars to become dirty and contaminated, which can reduce their conductivity and increase their resistance. To mitigate these environmental factors, consider the following measures. Firstly, maintain a stable temperature and humidity in the room where the busbar system is installed. Secondly, use corrosion-resistant materials for the busbars and connections. Thirdly, regularly clean the busbars to remove dirt and debris. Fourthly, use air filters to improve the air quality in the room. When performing electrical measurements, it is important to use calibrated equipment and to follow proper measurement techniques. Use a calibrated clamp-on ammeter to measure the current in each phase of the busbar system. Use a calibrated voltmeter to measure the voltage between phases and between phase and ground. Use a calibrated harmonic analyzer to measure the harmonic content of the voltage and current waveforms. Record all measurements and compare them to the manufacturer's specifications. If the measurements are outside of the specifications, take corrective action to resolve the problem. In addition to the above considerations, it is also important to consult with the manufacturer of the busbar system for specific troubleshooting recommendations. The manufacturer may have specific knowledge of the system and may be able to provide valuable assistance. Remember that safety is always a top priority when working on electrical systems. Wear appropriate personal protective equipment to energize the system before performing any work, and follow hospital safety protocols and lockout or tagout procedures. If you are not comfortable working on electrical systems, contact a qualified electrician. When dealing with vibration issues, especially in sensitive environments like hospitals, understanding vibration isolation techniques is crucial. Vibration isolation aims to minimize the transmission of vibration energy from a source to a receiver. Several techniques can be employed. Firstly, using resilient mounts involves placing resilient materials, such as rubber or springs, between the vibrating equipment and its support structure. These mounts absorb vibration energy and prevent it from being transmitted to the surrounding structure. Secondly, employing inertia bases involves placing the equipment on a massive concrete or steel base. The increased mass of the base reduces the amplitude of vibration and lowers the natural frequency of the system. Thirdly, implementing damping treatments involves applying damping materials to the vibrating surfaces. These materials absorb vibration energy and reduce the amplitude of vibration. Fourthly, using flexible connectors involves connecting the vibrating equipment to the surrounding piping or ductwork with flexible connectors. These connectors prevent the transmission of vibration energy through the rigid connections. When selecting vibration isolation techniques, it is important to consider the frequency of the vibration, the weight of the equipment, and the sensitivity of the surrounding environment. A vibration analysis can help to determine the best isolation techniques for a specific application. In addition to vibration isolation, vibration damping can also be used to reduce the amplitude of vibration. Vibration damping involves applying damping materials to the vibrating surfaces. These materials absorb vibration energy and convert it into heat. Several types of damping materials are available. Firstly, viscoelastic materials are polymers that exhibit both viscous and elastic properties. They are effective at damping vibrations over a wide range of frequencies. Secondly, constrained layer damping involves bonding a layer of damping material to a vibrating surface and then covering it with a stiff constraining layer. The constraining layer increases the stiffness of the damping material and improves its damping performance. Thirdly, tuned mass dampers are devices that are tuned to a specific frequency. They consist of a mass that is attached to a spring and damper. When the vibrating equipment vibrates at the tuned frequency, the tuned mass damper absorbs vibration energy and reduces the amplitude of vibration. When selecting damping materials, it is important to consider the frequency of the vibration, the temperature of the environment, and the desired damping performance. A vibration analysis can help to determine the best damping materials for a specific application. Another important aspect of troubleshooting a vibrating busbar system is to understand the role of resonance. Resonance occurs when the frequency of the vibration matches the natural frequency of the busbar system. When this happens, the amplitude of vibration can be greatly amplified. The natural frequency of a busbar system depends on its physical properties, such as its length, mass, and stiffness. The natural frequency can be calculated using mathematical formulas or measured using a vibration analyzer. To avoid resonance, it is important to ensure that the frequency of the vibration is not close to the natural frequency of the busbar system. This can be achieved by changing the operating speed of the equipment, adding damping materials, or modifying the physical properties of the busbar system. When troubleshooting a vibrating busbar system, it is also important to consider the possibility of fatigue failure. Fatigue failure occurs when a material is subjected to repeated stress, even if the stress is below the yield strength of the material. Over time, the material can develop cracks and eventually fail. Vibration can accelerate the fatigue process. To prevent fatigue failure, it is important to reduce the amplitude of vibration and to use materials that are resistant to fatigue. Regular inspection of the busbar system can help to identify any signs of fatigue failure, such as cracks or deformation. If any signs of fatigue failure are found, the affected component should be replaced immediately. When working on electrical systems, it is important to be aware of the potential hazards of arc flash. Arc flash is a dangerous electrical explosion that can occur when there is a short circuit in the air. Arc flash can cause severe burns, blindness, and even death. To protect yourself from arc flash, it is important to wear appropriate personal protective equipment, such as arc-rated clothing, gloves, and face shields. It is also important to follow safe work practices, such as de-energizing the system before performing any work and maintaining a safe distance from energized equipment. When troubleshooting a vibrating busbar system, it is important to be systematic and thorough. Start by gathering information about the problem, such as the location, frequency, and amplitude of the vibration. Then, perform a visual inspection of the system to identify any obvious problems, such as loose connections or damaged components. Next, take electrical measurements to identify any electrical imbalances or harmonic distortion. Finally, implement corrective actions to address the root cause of the vibration. Remember that safety is always the top priority when working on electrical systems. Wear appropriate personal protective equipment to energize the system before performing any work, and follow hospital safety protocols and lockout or tagout procedures. If you are not comfortable working on electrical systems, contact a qualified electrician. Regular monitoring of the busbar system can help to detect potential problems early. This can involve periodic visual inspections, electrical measurements, and vibration analysis. The frequency of monitoring should depend on the criticality of the system and the severity of the operating environment. The data collected during monitoring can be used to track trends and identify any changes that may indicate a potential problem. By implementing a proactive maintenance program, you can help to prevent vibration problems and ensure the safe and reliable operation of the bus bar system. In summary, troubleshooting a vibrating bus bar system requires a systematic approach that includes identifying possible causes, performing visual inspections and electrical measurements, implementing corrective actions, and following safety precautions. By understanding the underlying principles of vibration, resonance, and fatigue, you can effectively diagnose and resolve vibration problems and ensure the long-term reliability of the bus bar system.